remember we looked at, and I didn't forget, we did not calculate exactly we did not calculate the exact area for this between 0 and 4. We will today. We only found an estimate. And the estimate, remember, it was a rough estimate between 18 and 34. And we will be able to find the exact area. And you'll see in a minute how. But when we graphed last time this function between 0 and 4, it was something like this. So this is our f of x. And we used 4 subintervals. And we used the leftmost point, the rightmost point. One of them gave us an overestimate. The other one was an underestimate. But remember, we used n equals 4 subintervals. And what did I do? I determined an area using rectangles. So the area was basically the base, which is, we know, delta x. It was delta x multiplied by the function value at any point. So I'm going to say f of x. I'm going to put I because for the first subinterval is this height. For the second subinterval is this height, which is different. For the third, so it depends on where we're looking. When I is 1, the first subinterval will be this height, and the second one here, and the third one here, and the fourth one here. So I cannot just put f of x. It has to be specific. For the first interval is a value, for the second interval is a value, a different value, and so on and so forth. That's why we put I. And I is from 1 to 4 in this case. Okay, 4 subintervals. What if I have now 8 subintervals? Do you think with 8, will I get a better approximation of the area than I obtained it with 4? And then I'm going to ask, of course, what about 16? What about 32? So what happens when I increase the number of subintervals? Do I get a better estimate or not? What do you think? Will I get a better estimate with 8, 16, 32 than I had with 4? What do you think? Anybody, please. Your estimate.
Yes.
Yes, of course. Of course, because I will have less gaps. What concept from this class am I thinking about when I say n goes from 4 to 8 to 16 to 32 to 64 to 128? Which concept from this class that we worked on am I getting at by increasing the number of subintervals? What if I get n to go to infinity? Do you think that if n goes to infinity, will I have an exact area with no underestimation, overestimation? What do you think?
No.
The answer is yes. The more subintervals, the better the estimate. And if n goes to infinity, for sure there's going to be no error. No error. But what concept is this from what we studied so far in this class? Anything comes to mind?
Limits.
Thank you so much. Indeed. Indeed. So, the exact area. Thank you. Who said that?
I did.
Katie, thank you very much. Okay, very good. So, the exact area will be the limit as the number of subintervals goes to infinity from a sum of areas of rectangles. Of course, we don't write it like this. But what is the sum of the areas? Delta x times the height plus delta x times the height plus delta x times the height. So the areas of rectangles will be delta x times f of xi. You're not going to be tested on this notation. I just want you to understand what it means. So the areas of rectangles. And now the sum has a specific notation. What is this? It's the Greek letter S. Why don't we use S, our letter S? Because it's not convenient. So this is nothing else but Greek S. Why? Because it's so convenient to say here from n equals 1 to I. In other words, for when I is 1, I get delta x times f of x1. When I is 2, and this is the sum, a sum. In order to condense the notation, we are using the sum notation, the Greek S. I can write it like this. The limit as n approaches infinity from delta x times f of x1 plus delta x times f of x2 plus dot 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 plus f delta x, f of x, the last one, and n goes to infinity. Instead of writing it like this, we write it as limit as n approaches infinity from the sum from I equals 1 through n. That's better. From I equals 1 through n from delta x, f of xi. Nobody will test you on this notation. I just want you to understand the summation. This is called summation notation. What does it do? It condenses this into this. That's all it does. And it has different properties. This whole thing also has a name. It's the limit of the Riemann sum. What is this? That's all you need to remember. The exact area under the graph between such and such. We're not going to use the notation. We're going to use what it equals to, which is much easier to compute. We're not going to do anything with this notation. But I just want you to understand what it means. The exact area is obtained when the number of subintervals goes to infinity. So it's a limit of what? Of the sum of all areas of rectangles. And this is the area of one of them, base times height. So in condensed form, the exact area is the limit as the number of subintervals goes to infinity from the sum of all areas of all rectangles, base times height plus base times height plus base times height. That's all. And it's called the limit of the Riemann sum. And what it equals to is the exact area. Done. We're not going to use it. We're going to use something that it equals to. So what does it equal to now? So the exact area again equals the limit as n approaches infinity from the sum from I equals 1 from the first subinterval to the last one, delta x f of xi. But we are going to write it with the integral notation. The interval, the general interval a comma b, in our case it was 0, 4. In other case it was 0, 5. From a to b from f of x dx. What is this? What does it mean? Well, this is what we call the definite integral. What do you mean definite? It has definite limits. The one that we studied last time, I still have it here, does not have limits. They are called limits of integration. It does not. This is an indefinite integral. And the answer is always a function or a family of functions, the most general antiderivative. So this is the indefinite. This one is definite. It's clearly cut between this and this. And the answer is always a number. It's a number, not a family of functions, not the most general antiderivative. No, this is a number because it's an exact area. It's a numerical answer. Again, how do I read this? The definite integral, I'm going to write this down. The definite integral from a to b from f of x dx. So let me write this down for you. The definite integral from a to b from f of x dx. And the answer is a number. Again, we're not going to compute this. We're only going to compute this. Now the question is how? How to find a definite integral or calculate. Either find or calculate a definite integral. Okay, so that is now section 4.3. The fundamental theorem of calculus. The fundamental theorem of calculus has two parts. In part one, which we will not do anything with, I have to mention it, it's not in your book, but it's very important. We're not going to do anything with it, but I have to mention it. Part one states a very, very important topic, which is integration and differentiation are inverse operations. This is extremely important to remember. What does it mean? It means that if I differentiate an integral, this is a very important concept. So if I have the integral from f of x dx and I decide to differentiate it, this operation cancels this operation and I get the function back. Because differentiation and integration are inverse operations. Also, if I have the integral from f prime of x dx, I also get f of x because I'm integrating a derivative. Okay, so again, integration and differentiation are inverse operations. They cancel their effect on the function. This one cancels this one cancels this. Part two, it helps us calculate definite integrals, shows how to calculate the integral from a to b from f of x dx. How? If the function is denoted by lowercase f of x, the antiderivative will be denoted by uppercase f of x. So this is the antiderivative of f of x. I haven't finished. So I have the function, I find its antiderivative, and then a vertical bar from a to b, which states I have to evaluate the antiderivative at b and subtract when I evaluate the antiderivative at a. So again, the fundamental theorem of calculus has two parts. Part number one says, don't forget, integration and differentiation cancel their effect on the function. They cancel each other out. They're inverse operations. The second part, equally important, it tells us or teaches us how to calculate definite integrals. So how do I calculate the integral from a to b from f of x dx? First, I find the antiderivative of f of x, and then I evaluate it at b and a, and I subtract when I evaluate it at b minus when I evaluate it at a. So now finally, we can determine the exact area of the integral. If you remember, we had the function on 0, 4, and our function was x squared plus 1. So the area under the graph between 0 and 4 is the definite integral from 0 to 4 from f of x dx. Now it's a piece of cake. Which function prime is x squared? X to the third over 3. Which function prime is 1? X, put it in parentheses, vertical bar from 0 to 4. I plug in 4. I have 64 over 3 plus 4. When I plug in 0, minus when I plug in 0, everything is 0. This is 0, this is 0. So 3 times 4 is 12. So 76 over 3 is the exact area under the graph of x squared plus 1 between 0 and 4. Guaranteed. Our answer last time was anywhere, we just looked at that again, it was 18 to 34, something like that, with the leftmost point and the rightmost point. And this is the exact. Now, we're ready to calculate definite integrals. Let's go to the book. Okay, let me see the page number. Which page? 413, yes.